Okay. Good afternoon, everybody. Let's welcome Dr. Siva Reddy. He's a good friend of ours and a proud alumni of our Department of Meteorology and Oceanography. Dr. Siva Reddy is a young ocean data assimilation scientist who is working as a research scientist in King Abdullah University of Science and Technology, Kingdom of Saudi Arabia, with Professor Ibrahim Hototi, a renowned data assimilation expert. Siva Reddy is completed his master's in meteorology, and as well as he completed MTech atmospheric sciences also. Later, he was awarded from the Department of Meteorology Oceanography on study of data, global ocean analysis from a ocean data assimilation system and its sensitivity to observational and forcing fields for his Siva Reddy started his career in the University of Hyderabad as a research fellow under Professor K.V. Subbarao Garu in 2007, and as a project part of the project, he was placed in Inquiries, Hyderabad, to work on sea level variability and trends with Dr. M. Ravichandran Inquiries. Now he is a director of NCPOR Goa. Siva Reddy journey started with ocean data assimilation in year 2010, and assuming as a project scientist at Inquiries, he was very instrumental in developing the operational global ocean data assimilation system. The Inquiries GODAS, which was the first ever operational reanalysis system from India. He subsequently absorbed in Inquiries as a regular scientist to contribute to MOS monsoon mission objectives. As a part of the monsoon mission project, he and his colleague were deputed to University of Maryland, USA, to work closely with Professor Kalni. She's an expert for data assimilation and the local ensemble transform common filter. So they hard code the what called local ensemble transformed common filter technique to the high resolution regional ocean model in which we called ROMS. Again, the first ever such an effort from the India. Now both Inquiries and GODAS and ROMS are running on operational basis at Inquiries to provide global and regional ocean data assimilations and their forecast respectively. Currently, Siva Reddy is with Coast, Saudi Arabia, to develop a very high resolution operational ocean reanalysis system for Red Sea and Arabian Gulf. Dr. Siva Reddy has published 14 papers in a very reputed international journals, and he presented several papers in international and national conferences, and also he delivered several lectures on ocean data assimilation in international workshops, especially in the University of Hyderabad. Now he is with us online from CUSA to give us a talk on challenges in the ocean data assimilation. Let's welcome Dr. Siva Reddy.
Thank you, Professor Sunita Garu, for a nice introduction. And let me show my PPT first. Can you guys see the PPT?
Yes, yes.
Yeah, okay, great. Yeah. First of all, I would like to congratulate Professor Sunita Garu for organizing this wonderful webinar series successfully by bringing emerging and established scientists across India. See, this is not an easy task, so I really appreciate Professor Sunita for this. And I also thank her for extending invitation to me to be able to present in front of you all. It's a pleasure. And today my talk is on the challenges in ocean data assimilation. As many of you know, the outputs from ocean data assimilation, often referred as ocean reanalysis, they are used for various climate studies, like for example, to understand the El Nino, to better understand Indian Ocean dipoles, or even they are kind of, nowadays it's kind of necessary for providing improved ocean forecasts. And also, not only that, they're kind of necessary for providing forecasts using coupled ocean models to provide forecasts on monsoon, on seasonal, as well as extended rain scales. Well, so what these ocean reanalysis are usually prepared using data assimilation. Basically, data assimilation combines the model outputs with the observations to give the best possible state of the ocean. Well, we have a lot of ocean observation networks. If you look our observation networks, for example, from satellites, we have sea surface temperature, sea surface salinity. From altimeter, satellite altimetry, we have sea level anomalies. And for the in situ observations, we have wonderful global coverage of Argo, which basically provides the temperature and salinity from surface to the depth of 1,000 meters or 2,000 meters. And there are kind of tropical moorings, like, the tropical moorings, they are distributed between 10 south and 10 north, usually in the Indian Ocean as Rama, Tievo Pireta in Atlantic and the Pacific Oceans. And we have observations, in situ observations for currents from ADCPs or drifters. Our CODAs also give observations. And for sea level, we have tide gauge observations. There is no doubt these are absolutely valuable information. But what is the limitation? The limitation is that it is impossible to monitor the whole ocean, which is kind of, nowadays it's kind of, we need the complete picture of the ocean on almost on a real-time basis. For example, for coupled ocean atmospheric forecasting, or even for the improved ocean forecasts. Numerical ocean models, basically, they provide 3D picture of the state of the ocean. So they are based on primitive equations. These are those primitive equations. There are 7 equations. 3 are from the momentum equations and continuity, and the temperature and salinity equation, and equation of state. So when we want to use these equations in the computer, we actually need to discretize them, and we have to choose a resolution. When we are choosing the resolutions, so obviously we are missing something. What is that missing? They're kind of unresolved scales and processes. So we will be missing some processes purely due to the selection of the resolutions. And also, see, these models, they need us to specify some kind of parameters, kind of call, for example, we need to specify eddy viscosity terms. For example, these are horizontal eddy viscosity term, vertical eddy viscosity term, and horizontal diffusion, and for horizontal diffusion for temperature, salinity, and vertical diffusion for temperature and salinity. So these kind of parameters we need to specify. The thing is, these parameters, they depend on flow, and also they depend on resolution. So, and the knowledge on these parameters are not up to the mark. There is still gaps in knowing these perfect values for these parameters. Obviously, the numerical ocean models need inputs. What are those inputs? The inputs in terms of, we need initial conditions. We need the overlying atmosphere, the conditions of the atmosphere to drive the ocean. And if it is a regional model, we need ocean boundary conditions. Of course, we need bathymetry. So all these sources come with errors. They are like, how much ever you do, they are associated with errors. So all these errors accumulate and make our ocean forecast diverge away from the truth. So data assimilation acts exactly here, like to make the model forecast better. It makes use of the model forecast and the observations and gives us the best possible state by combining these two information. it is actually best understood with a 1D example. For example, here I'm showing a simple kind of 1D kind of plots. Let's say this is the time series of temperature at Vizag. Let's assume this as a temperature at Vizag. So the green line is the truth, which we never get to know the truth actually. Let's say we have sampled observations. Let's say we sampled the temperatures at various times. And let's say these black dots are observations. Remember, the observations have errors. They are not the truth. They come with some errors. That's why they are close to truth, but they're a little different. They can be on the truth as well. Fine. Now we want to let's say we have a 1D model for predicting the temperatures of Vizag, and for that model we obviously need to start from somewhere, and that somewhere is the initial condition, and the initial condition can have some error. And let's say I have started from here, and I integrate model forward. So what I want to do is I want to call data assimilation scheme to be able to correct my trajectories once in a while. Let's say I am calling the data assimilation every 24 hours. I stopped at the time t equals to 24 and grab the observations available within the assimilation window. So here we have, let's say we have 2 observations. We make data assimilation makes use of these 2 observations and the forecast available from your model. This combines and then gives a best possible state. In this case, only one temperature, that we call it as an analysis. And this update state will be used for the next model integration. Okay. So this is how the model progresses. And then again at time t equals to 48, just because we wanted assimilation to act every 24 hours, again the assimilation scheme will be called, and again we will get an update for our forecast. So we call it as analysis, and again it will the model will integrate from that updated state. So the cycle goes on like this. So this is how exactly the assimilation works. In this way, the model trajectories we are trying to bring close to the truth. So we just hope that the trajectories will become close to the truth after some time. Well, there are various data assimilation schemes available in literature, various assimilation schemes, but the most popular data assimilation schemes for ocean or atmospheric models are listed here, like optimal interpolation, 3D VAR, 4D VAR, and ensemble Kalman filters. And in ensemble Kalman filters, we have ensemble optimal interpolation, ensemble adjustment Kalman filter, local ensemble transform Kalman filter. All these are kind of examples for ensemble Kalman filters. And all these data assimilation schemes, they try to solve this particular equation. This is the fundamental formula for data assimilation. So what is the formula? The formula is the equation is something like this, like XA is equals to XF plus K multiplies by Y minus HXF, where K is a Kalman gain given by BH transpose and HBH transfer plus R whole inverse. So what are the terms? What are the different terms? XA is analysis. This is what we need. We want from the data assimilation scheme. And XF is your model forecast. Like for example, in the earlier case, the forecast at time t equals to 4. So that's our forecast. We want an update for this forecast, and here Y is observations, like temperature observations or whatever. H is transformation operator. What it does, it transforms the model space to transfers the model state to the observation space. It's kind of, you can think of it as a interpolation, simple interpolation operator, So to bring to the observation. And B is your forecast error covariance or background error covariance. I would use the term forecast error covariance or background error covariance. They are both are kind of similar. So what it is, it basically encompasses all the errors associated with XF. So the B contains the errors associated with your model. It tells you about the model errors and also the model error covariances. Like if a particular location has some error, what is the dependence of the error on some other grid point, something like that. I will come back to this. Again, you will understand it better. R is your observations error covariance, similar to a forecast error covariance. This is R is observations error covariance. R encompasses all the errors associated with innovation term. We call Y minus H XF is the innovation. So remember, the R encompasses errors and the error covariances associated with the term Y minus HXF. It's not the error associated with the simple observations. No, it's error associated with the innovation term. Let's try to get a feel of different elements and the role of different elements in these equations. So again, the best way is to take some simple examples and try to understand. Here, I take the same example, like just a slide back, what I have shown, the same figure. Here, let's say I want to write down the equations for the analysis time at t equals to 24. See, this is a temperature, truth, temperature of Vizag, model, observations. So since I have the 1D model, so I have, only one variable, XF, and I have, in the assimilation window, I have two observations, right? Excuse me 1 minute. So I have two observations here. So my observation vector is Y is Y1 and Y2. And for the simplicity, I'm just assuming that these observations are available exactly at time t equals to 24. Though they are not available at the time t equals to 24, I'm just assuming for the simplicity that they are available at time t equals to 24, these two observations. So the H is going to be 1, 1. And I need few more information. Was that the background error covariance? Here in this 1D model, it is just one variable. So the background error covariance is going to be, it's just the model error, it's just a model error. And R is observation error covariance, is a 2x2 matrix. And what it contains? It contains R1, RC, RC, and R2. What is R1? R1 is your observation error variance of observation Y1. R2 is observation error variance of observation Y2. And what is RC? RC is your covariance between the observation errors. Covariance between the observation errors of these two observations. What does it mean? It means, so let's say you are using a same instrument to sample the observations of these two observations. You can always have a chance that when the instrument commits an error here, most likely it can commit a similar error, or some kind of correlation can always be there to commit an error for observation Y2. So the RC gives information about such thing. Okay, error covariances. Now we have everything. Let's put it in the equation. See, these are the same thing, right? XF, Y, and everything is same. Now I am putting all these things in this equation to get Kalman gain. K. The K in this case is kind of a 2 by 1 matrix, it's a vector. So how does it look like? It looks like this. It is.
Sorry, Dr. Reddy. Yeah,
Yes.
excuse me. Actually, yeah, your voice is sometimes getting disturbed by sometimes. So please take care of that.
Okay. Can you hold for some time so that I can, I will use my.
It's okay. It's okay.
Headphones.
Thank you.
Yeah, just me. Sorry, a little pause. Yes. Please excuse me for this. Can you hear me?
Yes. Go ahead.
I think it's. I think it is. Please excuse me. I think I need to disconnect something from here. Just a minute. I'm sorry for that.
Yes, all the participants, please mute your mics and videos. Please switch off your videos.
I'm sorry for this.
Okay, carry on.
Yeah, I didn't prepare for this. Perhaps with this it will be much better.
Absolutely fine.
Yeah. Now, I hope you are able to hear me.
Yeah, it's absolutely fine. You go ahead, please.
Yes, excellent. So now, yeah. So now my Kalman gain is something like this. BR2 minus BRC divided by BR1 plus BR2 plus R1R2 minus 2BRC minus RC square and the other term. What it actually saying that the Kalman gain is determined by the forecast error variance B, and the observation error variances R2 and R1, and also the observation error covariance. So this is how the 1D problem we can see. And from this equation, you can very easily understand that when the B is 0, that means you have, when B is 0, the meaning that you have full confidence on your model. When the B is 0, you are actually, the Kalman gain going to be 0. That means you do not have any update. Okay, and take the another scenario where your B is much greater than observation errors. That means your model error is much larger than observation errors. In that case, your Kalman gain going to be determined by this matrix, something like this: R2 minus RC by R1 plus R2 minus 2RC and the other term. So basically what it says, the Kalman gain is determined by diagonal and off-diagonal elements. So when your model error is too large, your update going to be determined fully by your observations. And in that observations, the observation error variance and also the observation error correlation, covariance, that also is there. Please remember this, we will come back to this. Well, let's understand about what the forecast error covariance does. Forecast error covariance B matrix. In this case, let's take a 2D example, a simple 2D example. Let's say this is your model domain with a grid. Let's say you have 9 grid points. Like let's say this is a temperature at first grid point, 2, second grid point, 3, and so on, 9. So in this case, your forecast, your state vector, model state vector going to be something like this, like the temperature at first grid point, like x1f, x2f, x3f, and so on, x9f. So this is your forecast state. Let us assume that you have an observation exactly at the grid point 3. So just to make things easy, I'm just assuming that the observation is exactly available at 3, and I have a temperature observation for a temperature model. So for that, like y is equals to y1, and my h going to be, in this case, my h going to be 0, 0, 1, 0, 0, 0, 0, 0, 0. So that means when I operate h on xf, I would get x3f, right? Fine. I need further information. What is that information? I need to know how does my model forecast error covariance look like? So what are the different elements in model error covariance? I would need information about what is the model error at grid point 1, grid point 2, grid point 3, and so on, grid point 9. Once I get that information, I would put all of them in the diagonal elements. See, the B11, B22, B33, all these are model error variances, basically your model errors, right? And I need another information as well. So what is that? That information is like, what is the contribution of the model error at grid point 2 on grid point 1? Contribution of model error at grid point 3 on 1, 4 on 1, 5 on 1, something like that. So I need that information as well. I would put them in the first column. In the same way for grid point 2, third column. In the same way for grid point 3, third column, and so on, 9 columns, right? Fine. So now I have got the forecast error covariance. Since I have only one observation, I have the observation error variance, the R1 responds to Y1. Now I got all information. Let's plug it in this equation. What I would see, what I'm seeing here is my analysis vector x1a, x2a, x3, and so on, x9a is equals to the forecast vector x1f, x2f, x3f, and so on, x9f, plus some vector. What is that? B13, B23, B33, and so on, B93. And this is innovation y1 minus x3f by B33 plus R1. Here B33 is your model error at grid point 3, basically. Observation error of observation y1. This is your observation. This is your model forecast at grid point 3. And what are these? I just explained to you. These are the model error covariances between the grid point 3 and 1, grid point 3 and 2, grid point 3 and 4, grid point 3 and 5, okay, and so on, 3 and 9. So what you can notice here is that you have only one observation, and that too at grid point 3. But what you have got is you have got update at each and every grid point of your model. Like for example, x1a, you do not have observation, but still you have got an update. x11, x1f plus b13 into something. x2a equals to x2f plus b23 into this. So you have got update for each and every grid point. So this is the role of forecast error covariance. Basically what it does, it propagates observation information from one point to the other. So this is what it does. So we have covered all the kind of different kind of elements and how they look like. Now let's see how the Gaussian data assimilation system, the flowchart of it look like. Let's say you have a Gaussian model, simple normal Gaussian model, anything, modular Gaussian model or ROMs or anything. It actually need initial condition, right? Let's say at time t equals to 0, you have the state the ocean state, like temperature, salinity, sea level, and currents in the all 3 dimensions. And the atmospheric forcing, let's say you have 24-hour, for the next 24-hour, the atmospheric conditions. With these 2 pieces of information, you would run your model and you would get output. So these are, we call them as forecasts. Let's say I have a forecast at at time t equals to 24 hour. If you do not have any assimilation, this forecast, this output will be used for the next model integration. And the model will run with the next atmospheric condition, atmospheric forcing, and it will give outputs. The cycle goes on like this. When you have assimilation, what happens is the output at time t equals to 24, for example, it will be fed to the data assimilation scheme. And the data assimilation scheme would take observations from the all assimilation window. For example, the observations can be from the temperature and salinity profiles from Argo, Rama, or currents from drifters, and so on. So it combines these 2 information and gives us the best possible state of the ocean. We call them as analysis, okay? And this analysis, which corresponds to time t equals to 24, will be fed as updated state to the next model integration. And the ocean model will run with this updated state, and it will give output, it will give forecast for time t equals to 48. And this forecast will be again fed to the data assimilation scheme. So the cycle goes on. So this is how usual data assimilation systems work. Now it's time to talk about the challenges related to various elements. Here now I want to talk about the challenges related to the observation error covariance matrix. Okay. Before that, I want to introduce you about the observation error in the context of data assimilation. So the observation error basically associated with, as I told earlier, it associated with y minus hxf. So to understand it, let's assume this is the real world. Let's say this is a cyclone. Okay. I want to sample observations. I would sample it with some kind of instrument. It can be radio sonde, or it can be, from satellites, anything. When you sample the observations, you would obviously, depending on your instrument, you would have measurement errors, and depending on your instrument, you will have pre-processing errors. Pre-processing errors. For example, if you are measuring with the satellites always, measure radiances, and you have to derive your parameter from those radiances using some algorithm. So the algorithm can always have some kind of error. So we call them pre-processing errors. Okay. Next, the next term, HXF. How we would do with that? Let's say this is the real world. This picture is the same as this, but in the resolvable scales of the model. Remember, we cannot run our model like whatever resolution we want. We always compromise on resolutions, like let's say 1 degree resolution, something like that. So let's say this is the real world, same picture in the resolvable scales of the model, right? So we are actually taking HXF from this. So obviously we will have errors. First of all, errors associated with the transformation operator H. And another thing, the errors associated with unresolvable scales and process. You can see the large differences, right? They both are truth, but one is the resolvable scales of the model. You can see the large differences. This is simply due to the unresolved scales and processes. So the observation error in the context of data assimilation, the total observation error consists of 4 terms: measurement error, pre-processing errors, error associated with the transformation operator H, and errors are due to unresolvable scales and processes. So these three terms, the last three terms, are often referred as representation errors in the ocean or atmospheric data assimilation. And remember, in the ocean, especially when we are assimilating in situ temperature and salinity, all other errors are kind of very small, like the measurement errors. For example, if you're assimilating Argo observations, you have the measurement errors are something like 0.005, very, very, very less. And the pre-processing errors, nothing. And H, nothing. But the errors due to unresolvable scales and processes is the largest contributor, and it is large, okay, for the in situ observations. And it is very easy, actually, to understand that these observation errors does have variations in space and time. You don't believe me? I will show some results from our QJRMS paper published in 2019. This is, for example, temperature representation, temperature observation errors. I would call representation errors or observation errors. They both are almost similar in this particular case. So here what I'm showing is the temperature errors in the different regions. This is the panel A is for the Great Whale region, South Equatorial Current region, South Madagascar Current region. So this is a depth and this is a time. And these are the temperature errors. What you can see, for example, if you focus at 120 meters depth, what you would see is temperature errors, observation errors have seasonality. For example, during summer, you have observation errors something like 1.6 degrees centigrade, and during winter it is less. And they are particularly large at 120 meter, and at other depths it's somewhat smaller. And further, it has interannual variability as well. Like for example, here you could see large errors, and the other years it's not that much. So there is interannual variability as well. So it has time variations and the depth variations. And it also has spatial variations. You see, for example, here, you do not have large seasonal variability, but you have large interannual variability compared to seasonal. So it has a space and time, like observation errors vary in space and time. And also, actually, they also vary with the flow. Like whenever there is an eddy, you would generally have a lot of observation errors. You know why I'm saying this? Often the ocean data assimilation scientists or the atmospheric data assimilation scientists tend to assume that the observation errors are static over time. Why so? Why people do like that? Because it's really difficult to estimate these. Not much research has gone to it, actually. Poor knowledge of these observation errors evolution. We want to show how impactful are they. So, for example, these are the results from the assimilation experiments. The left panel, the left panel shows sea surface height difference in RMSDs in sea surface height. The difference is between the assimilation and free run. Here we assimilate a temperature, in situ temperature and salinity observations, and also SST. We assimilate temperature and salinity observations with constant or the static observation errors. Okay. So here the positive values indicate degradation with assimilation. Positive value, degradation. Negative value, improvement. The blue ones are improvements, orange ones are degradations. What you can see is, overall with the assimilation, you would see improvements even for the static case. But the thing is, when you incorporate that flow dependent observation errors, for example, here this is the same figure, but here in this assimilation experiment, we incorporate dynamic arrays, or in the other way, the flow dependent representation errors. What you would see is a lot of improvements, So it's like wonderful improvements. It's like something like 9 centimeter improvement compared to the free run, larger than what we have got with the static experiment. So this is the kind of impact the flow dependent observation errors have on the simulations. Well, now we have a tendency that the more observations, the good for data assimilation. Is it really true? Actually, it has terms and conditions, actually. So I would say, yes, more observation is good for assimilation, but only if assimilated properly. Why I'm saying this? Let us know that all the Gaussian data assimilation system actually neglect observation error correlations. Why? Because they are poorly known. In order to understand that better, let us focus on this figure. This is the figure from Zhua et al. 2017. This is basically from the ECMWF analysis system. These results are using the ECMWF reanalysis system. So here what they were showing is the temperature RMSEs corresponding to the whole globe. Okay, temperature RMSEs corresponding whole globe according to the depth. Okay, and this is for same thing for salinity. So 3 experiments they show. So the first experiment is no SLA, where no SLA observations are assimilated. That is the green line. And another experiment where you assimilate all observations, all sea level observations. So that is, the red line is the no superop experiment, where you use all the sea level observations, all. And the blue line is an experiment where is a superop experiment, where you actually discarded a considerable amount of data. What you would see in these plots is that the red line, which corresponds to the assimilation experiment where you used all available sea level observations, that is actually degrading compared to no SLA observation experiment. Whereas the blue experiment where you discarded the considerable amount of data is improving compared to the no SLA. Why it is so? It is because in the satellite sea level observation, you really have these observation error correlations. They are really there. And when you neglect these, and especially when the observations are correlated greater than, let's say, typical 0.2, then you are screwing up when you are using all the observations. So the best remedy people found was to discard the considerable amount of data so that we somehow avoid these observation error correlations. Here again, this is a problem, right? Like we have a lot of observations from satellites with all kinds of efforts, and we are unable to fully use this observation. There's a problem. We have to do something with this, right? That's something, if we work on these observation error correlations, it's what, it's a challenging task and research problem. More can be done. Now, let's talk about the challenges related to the background error covariance in Gaussian data assimilation systems. I want to talk about the background error covariance in 3D VARs or 4D VAR and optimal interpolations. Usually in these systems, B is prescribed. It is usually an educated guess. The model errors are they're educated guess. And another thing is the cross correlations, that B12, B13, those things are assumed to follow some predetermined structure. For example, this is a figure from Behringer et al. 1998. This is from the system Global Ocean Data Assimilation System at Ensemble. In fact, these are the error correlations used in INCOIS-GODAS as well. For example, this is the cross correlations in the Pacific Ocean. If you focus at the equator, the cross correlations, actually they are largest at this point and decreases as you go farther from it there. That's how the error correlation structures are defined. They are predefined. This can be a problem. They doesn't vary over time. They doesn't vary over time, and it can be a problem. Why? Because these error correlations, they doesn't, they usually vary in time, in reality. I will come back to this. You will understand it in the next few slides. And another thing is, and B is univariate in 3D VAR, 4D VAR, and optimal interpolations. What does it mean? This means that, for example, you are assimilating temperature observations. You have only temperature observations. You are assimilating temperature observations. You will be getting an update for temperature, your model temperature variable. That's it. You wouldn't get any update for salinity. You wouldn't get any update for your sea level or your currents. This is actually a problem. Why? Because when you get an update for your temperature, you have to somehow, you should have some update for your other parameters, other variables, because your ocean state is supposed to be dynamically consistent. You know, your model, when you are running your model, all these are like, you know, dynamically connected. And when you are correcting something and not correcting something, you are screwing up. This is an example. This is from our paper published in Ocean Modeling in 2013. This is, for example, results are from INCOIS-GODAS. This is a 3D VAR data assimilation system. And here we assimilate sea surface temperature and in situ temperature and salinity observations. Here, what I'm showing is differences between the current speeds from the free model and the observation. Consider Oscar as an observation for time being. Free model and Oscar. And the vectors are the current vectors, the differences. So these are the climatological differences for example, for the season January, February, March. And this corresponds to April, May, June, July, August, October, November. This plot shows for the Indian Ocean, equatorial Indian Ocean. What you would see is some differences. Can speak, you have some differences, fine. But this right panel is a similar thing, but from the assimilation run. What you were seeing here is the differences have increased like anything. You know, the differences are larger. Why? Because the 3D VAR system did not have the multivariate relations. We were assimilating temperature and salinity, and what happens to currents is what happens. It's like you are increasing errors. Well, people have come up with some kind of remedies to account for multivariate relations in these kind of systems. Some of the operational centers like UK Met Office or ECMWF, they adopt a balance scheme proposed by Weaver et al. 2005. They are basically based on some dynamical properties of the ocean to account for multivariate relations. They look something like this. The equations look something like this. What they do is the correction, the temperature correction would be the correction directly from the assimilation. It's perfectly fine. But for the other variables, for example, for salinity, sea level, U and V, you have two terms. One is the balance correction, they call as a balance correction delta SB. and delta SU. This is unbalanced correction. So like that, you have for each and everything balanced correction, unbalanced correction. What is unbalanced correction? Unbalanced correction is directly from your assimilation update, and the balanced correction is based on some properties, dynamical properties of the version. For example, the balanced part of salinity correction assumes that water mass properties doesn't vary over the assimilation window. That means it makes use of the TS relation. Temperature and salinity, they doesn't vary over the assimilation window. This is the assumption. Similarly, based on that assumption, they get the balance, the correction for the balanced term. Similarly, for currents, they make use of the geostrophic relation. They get correction based on geostrophic relation. Well, there can be problems. Why? The temperature salinity relation doesn't hold for water mass formation regions. For example, in the North Atlantic, there are a lot of water masses forms there. TS relation, it is not valid. And also in the North Red Sea, water mass, it's a water mass formation region. It's not valid. There will be a problem, more problems there in such regions actually. And do you really think the geostrophy is predominant everywhere in the ocean? I don't think so. It's like there can be regions where a geostrophy is pronounced. There can be regions, and in these regions, you are actually screwing up. Okay. Well, this appears to be a kind of a solution, but there can be more you can do with these multivariate relations in 3D VARs or 4D VARs or optimal interpolations. Well, this problem is not at all an issue in ensemble data assimilation. Why? Because the multivariate relations are basically well taken care in ensemble data assimilation by using the ensemble. They actually compute the multivariate statistics and assimilate. So let me show you, before we forget, that I want to show this figure, what happens in an ensemble data assimilation for a case which is similar to what I have shown earlier with the 3D VAR. So here, these are the results from our paper published in Ocean Modeling in 2019 using LETKF ROMS. ROMS is a regional ocean model, and LETKF is an ensemble data assimilation scheme. Sorry. And we assimilate sea surface temperature and in situ temperature and salinity observations. So this plot, the left one, is the difference in current speeds between the free model and the Oscar, and for different seasons: January, February, March, April, May, June, July, August, and October, November. And this is the same plot except from the assimilation experiment. What you would see is differences. What you see in the free model are reduced. They are very less. Whereas if you remember in the 3D VAR systems, they are increased with assimilation. Here it is decreased. So this is the kind of advantage you have with the ensemble data assimilation. These are very naturally taken care, the multivariate relationship. Here now I want to show you the typical flow chart of ensemble Kalman filter data assimilation systems. Here, all such beautiful things, the multivariate relations and the flow-dependent nature of the background error covariance are very well taken care using this strategy. Like, so what happens in ensemble data assimilation is that instead of using a single initial condition, you would use an ensemble of initial conditions. Like you would use X1A, X2A, and so on, XKA. It can be a 50-member ensemble, 100-member, 1,000, whatever. Ensemble of initial condition. And you can use different models like MIT-GCM1, MIT-GCM2, and so on, MIT-GCM-K. And each model can differ in terms of the initial condition it uses, or the atmospheric, different atmospheric forcing it uses, or the different physics it uses, or the combination of all these two. So what happens is it basically gives you an ensemble of forecasts, right? In a way, it is to say that you are not only giving the temperature, for example, you are not only giving the temperature of Vizag as 30 degrees centigrade, you are also saying the temperature like 30 plus or minus 2 with a kind of certainty, like it can not go beyond 30 plus or minus 2 with kind of uncertainty, with complete information you are saying with this ensemble, right? So this ensemble you would feed to the ensemble Kalman filter, and the ensemble Kalman filter use observations, and the ensemble Kalman filter computes the statistics about the multivariate relations from the ensemble itself, and also it computes all the off-diagonal elements of background error covariance and the diagonal elements of background error covariance. All such things are automatically created, computed in ensemble Kalman filters, and it will give us the analysis ensemble. And this analysis ensemble will be used for the next model integrations, and again, the Gaussian model ensemble will run and give forecast ensemble, and the cycle goes on. So this is how you are actually evolving, and you are getting a flow dependent background error covariance, right? So that's a ensemble Kalman filter gives such a beautiful beautiful thing. At least it has those capabilities. Well, there are challenges in ensemble data assimilation as well, mainly associated with the limited ensembles. Usually the ensemble methods, they assume Gaussian distribution in the prior ensemble. What does it mean? For example, see, this is from the Gaussian dynamics paper published by our colleagues in KAUST. So here, let's say my SST prior histogram at the South Red Sea. South Red Sea is here. Let's say if you plot the histogram of SST from the prior ensemble from a 1,000-member MIT GCM dot system. MIT GCM dot is an ensemble-based assimilation system using 1,000 members here. What you would see is a very nice kind of close, the Gaussian kind of structure is seen. Nice, fine. The same system when you run with the 100 members, well, there is some Gaussianity is there, but it's not as tight as 1,000 members, right? So it's a problem. What happens if you do not have the Gaussian distribution? Basically, when you do not have Gaussian distribution, your solutions cannot be unique. You cannot get a unique solution. That's a problem. Further, there is an issue with the limited ensembles. That is, they generate spurious correlations. For example, again, here I'm showing the ensemble correlations in the prior between the correlation between this point and other grid points, right? In other words, what I'm trying to say here is, for example, you have an observation here at this block dot. It will be influencing influencing the ocean state all over these places, all over. But it doesn't influence, it doesn't have any influence in the northern Red Sea, in these parts, right? This is the case with the 1,000 members. And it's most likely true. And with the 100 members, let's say you have observation here. it will influence here as well as in the Northern Red Sea. Why? Because it has spurious correlations. This does not seem to be correct, right? So spurious correlations is a problem with the limited ensembles. And we have to live with limited ensembles. We cannot run a 1,000-member system because computationally it's not practical. So this is a serious problem in ensemble data assimilations. However, we come up with some kind of solutions for these spurious correlations. A beautiful concept actually, an easy localization. What localization does? The localization restricts the influence of observation within a particular radius. Let us say you have, let's say these are the model grid points, and you have observation, the cross. Let's say you have observation here, and you would say that this observation can influence all the grid points at the most within this radius. You wouldn't get any update for these grid points outside this radius. This is simple and effective. So this would solve most of the issues, but there are still a possibility that these are insufficient to, it basically creates additional problems in some situations. What are those situations? These are the results from our Nature Scientific Reports paper. Here I have simulated the observations, the time series observations like mode by case. These are all the temperature. Let's say my temperature and salinity observations are distributed like this. And I assimilate these observations in LETKF-NEMO assimilation system and compare it with the observations. And compare, basically I compare with respect to the free run. So here I'm seeing the results from the assimilation experiment, the impact of assimilation on sea surface temperature, for example. So here, this is a difference in RMSDs between the assimilation run and the free run. Here, the positive indicates the degradation with assimilation and negative indicates improvements with assimilation. This is for SST, this is for SSH. What you can see is, well, with the assimilation, you are improving within this band, observation band. Wherever the observations are there, you are actually improving. But what are these? You are actually degrading. And these degradations are very large in terms of SSH or even in terms of SST. Just above your boundaries, you are actually degrading your ocean forecasts significantly. So this is a problem with the localization. So a better localization schemes might help. More research needs to be done to avoid this kind of issues. Well, importance of accounting for uncertainties. The ensemble Kalman filters tend to lose their spread quickly. And when they lose their spread, they do more harm than good. Here, these are the results from our latest paper published in GGR. Here, I am showing the sea surface salinity map from a free run. This is sea surface salinity averaged between 15th September to 8th October 2011. This is the sea surface salinity map from the free run. And the dots you see are actually the observations, in situ observations from research crews during that time. Okay, when you compare these two, when the observations are well matched, you can understand that the background sea surface salinity map or your simulation is good. You can understand in that way. So this is the same sea surface salinity map after assimilation. I assimilate sea surface temperature, in situ temperature and salinity, and sea level. Okay, and these observations I kept for independent evaluation. So this is the result from assimilation experiment when I accounted uncertainties only from initial conditions. What you were seeing from this assimilation experiment is that the differences between the observations and your the forecast from the assimilation run are very, very large. They are kind of spurious, and they are very, very large, larger than free run. You know, that's what I was saying. They can do more harm than good when not done properly. This is the same thing. This plot is the same sea surface salinity map from the assimilation run, but this time I account the uncertainties from not only from ice initial conditions, but from atmospheric forcing and model physics. In a way, I'm not only using the initial ensemble for the initial conditions, but I am using ensemble for atmospheric forcing, also ensemble of model physics. So basically, I am evolving my background error covariance in a very neat way. So when you do like that, absolutely wonderful. It does much better than the free run and no signs of kind of degradations. It's wonderful. What it says, it's like the integrating the system with ensemble of atmospheric forcing and model physics are like, in that case, integrating it with all kind of uncertainties is so important. This kind of thing is an additional burden in terms of computational storage, and also in terms of, it's tough to to incorporate all kind of uncertainties. So more research needs to be done, and there is a lot of scope for improvements. Well, tides assimilation. We all know that tides in the ocean, they typically exhibit strong diurnal and semi-diurnal variability. Before discussing further, I want to show here the tidal oscillations, tidal heights at Anbu, one of the location in the Red Sea. So this plot is actually harmonic analysis done on this. So here I'm showing the time series of the tidal heights for a month, so starting from February 10th to March 10th. What you would see is the black line is from the tide gauge. Red line is from Otis. Otis is a product based on the inverse model, where the tides are basically they climb that they assimilate. The blue line is from the MIT GCM 2 kilometer model. So what you would see is you can very clearly see there are like the diurnal variations, right? And there are kind of differences between Otis and tide gauge or MIT GCM and tide gauge. Why this kind of differences? Usually this kind of differences usually occur mostly because of the poor representation of bathymetry. This is one of the major factor for poor simulation of tides in ocean models. So in order to assimilate, we may be able to assimilate these tides, but what we need is we may be able to assimilate these with the 4D assimilation, meaning that we need to compare the model forecasts exactly at observation time. You remember when we are comparing the when we are using the assimilation window, we were assuming that observations are taken exactly at the analysis time. That is because we only have one ensemble for time t equals to 24. So for this kind of types assimilation, we might need an ensemble at time t equals to 1, 2, 3, and so on, 24. You know, all those things. So computationally, it's very tough to get all such things. Not only that, we also need to be able to account for errors or account for uncertainties in bathymetry, which is tough. Nobody has done this. It's a research problem. This is a challenging, and nobody has assimilated tides in their ocean models yet. Why? These are the major reasons. Well, this is a summary of the challenges in ocean data assimilation I talked about. Yes, the flow-dependent observation errors is a challenging task. Yes, we did estimate these, but more can be done. More research has to be done because there is a great improvements if we incorporate this. Observation error correlation, absolutely no research is done, or not much work is done in this particular case. So more research needs to be done for observation error correlation. Tides assimilation I described. We have to, you know, account for uncertainties in bathymetry, and more importantly, we have to fight with the computational resources. And if you are still a favorite of 3D VAS or 4D VAS or optimal interpolation data assimilation systems, I would only say one thing: best of luck. Because the multivariate relations are still a problem, and you have to fight with it. You have to, you know, work more on that. Obviously, alternatives for Gaussian approximation is needed, and effective localization functions. I don't know whether anybody is working on this, but I don't know, much more research has to be done for effective localization functions. And accounting for all sources of uncertainty is always a tedious task, and not much research has gone into this. So it's equally challenging. And two more things I want to specify here. I haven't discussed in my slides, but it's worth mentioning here, is that the data assimilation systems can be used for advocating the future observation networks. For example, you will be able to tell where exactly you need observations. You know, what are the optimal locations for the observations? It will save a lot of money. You know. And in the similar way, see, there's nobody in India has worked on this. It's worth trying this. And another important thing, and nobody focused on this in India, not many researchers across the world, is that we can actually estimate model parameters, like model diffusivity coefficients, viscosity coefficients. We can actually estimate using data assimilation systems. Right? Somebody interested in reading further? So here are the textbooks and the review papers. This is the bibliography. And thank you very much for listening to me and for your kind patience. That's all I have. Thank you.
Thank you, Shiva, for your excellent and extempo presentation on challenges in the ocean data assimilation. Any questions from the participant side? Anybody? I hope everybody is silent.
Do we have any notable observations on Red Sea?
Sorry, sir.
Do we have any notable observations on the Red Sea?
Shiva, your mic is not working. No, your mic is not working.
Hello? Are you getting me?
Your voice is audible, sir, but Siva voice is not audible.
Yeah. Some loose contact, I think, at his end. It is showing mic on, but voice is not coming.
Yes, 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 yes. I have some questions for. No, your voice is not audible. Yeah, he will be back. He will be back within.
Guys, can you hear me now?
Yeah.
Yeah.
Excellent. Yeah. Sir, coming back to your question, so I think you have asked whether you have any observations in the Red Sea.
Yeah,
Yes, we do
notable
have.
observations.
We do have observations for sea surface temperature from satellites and sea level observations and few temperature and salinity observations, in situ temperature and salinity observations. But not that many, but few observations. Yes, we have. The one I was referring to was in 2011. So we have some one or two Argo observations, especially in the Gulf of Aden, and there are kind of research cruise observations. We have.
What is the tidal effect on this Red Sea with its limited space?
The tidal heights are not that large when we compare to the Bay of Bengal or to the Arabian Sea. You see, even in my plot, what I showed, there you see like, diurnal variation, something like 30 centimeters. That's it. It's very less. But even then, the problem is, the thing what I wanted to highlight is, even that we are unable to capture well, especially the spring tide. And this is the problem with the data assimilation, like we are unable to do it.
To what extent the wave height is probable there?
I have no idea, sir. Actually, my colleagues are working on this wave height thing. Dr. Sabik, I have no idea on this waves and all that. Yeah.
You have a good survey of bathymetry within that limited space?
Sir, our colleagues, they use JEPCO, and they have some Navi-based bathymetry as well. So they merged these two. And yeah, you can always understand that there can still be more can be done for the bathymetry, but see, they mainly based on JEPCO and some naval data. So
okay, thank you.
Yeah.
There is a question from Karunakar. How is the radius of influence computed in localization process? Is the radius of influence is always fixed? That is his question.
Yes, indeed. In the ensemble Kalman filter, yes, it is a localization radius is kind of fixed. Something like, we fix like 300 kilometers, something of that order. And we use, it's not a simple localization radius. I would say it's kind of, what is the function? Gauss cone function we fit. So the short answer is yes, it is kind of a fixed 300 kilometer.
Okay. I have one question as a layman. So if you do the ocean data assimilation, so what are the prerequisites conditions for coastal activities and biological activities in general?
What do you mean? I did not understand the question well, I guess.
So it requires some prerequisite conditions for data assimilation, especially when we are doing assimilation on coastals and biological.
Okay.
So,
Okay. So first and foremost, we need good observations. Good observation is the key, and also we need a reasonable model. We need a reasonable model. We cannot work with an unreasonable model. No.
okay.
So, yeah.
And one more question. So what is the role of atmospheric forcing when you do like waves, Rossby waves, or atmospheric perturbations, whatever stability criteria?
A lot of influence.
Yes.
Lot of influence, actually. Even in the assimilation system, they have a lot of influence. Atmospheric forcing has a lot of influence on the model simulations. So, a lot.
Okay. So,
Yeah.
what is the best method of data assimilation when you consider different satellite products you have? So,
Yeah.
what is the best method to estimate?
Yes. To me now, obviously it is very tough to answer, but what I would say is if there is a competition between ensemble Kalman filters and 3D VAR and so, I would choose ensemble Kalman filters, because the framework of the ensemble Kalman filter is so beautiful, and if I do not need to worry about these multivariate relationships or the flow dependent nature of the background error covariances. These are the basic limitations of 3D VARs or 4D VARs or optimal interpolations. So I would prefer ensemble Kalman filters. Any kind of ensemble Kalman filter like EAKF, LETKF, they are the same. The effect is same.
Okay.
Yeah.
Sir, you are asking any questions, Parav sir?
No, no more.
Okay, then fine. So if there are no questions, let us thank you, Dr. Sivareddy, for your wonderful, wonderful interaction with us, and sincere thanks to your time, valuable time. It is a lot to us, and my special thanks to Professor Ibrahim Hototi, who is joining us in this webinar. Special sincere thanks to him, and hope our student community will inspire you by watching your lectures and everything. So they will keep on going through your guidance. Okay. Thank you very much. Thank you so much.
Thank you very much for this opportunity, and thank you all for listening to me.
Thank you.
Thank you.
Tomorrow at 11 o'clock. Tomorrow.
Dear participants, tomorrow we will meet again at 11 o'clock. There is a talk on Krishna Kishore. Most probably he will be available or evening. We don't know exactly. There is a slight deviation of the actual program. We'll see. But
Okay,
the program is scheduled at 11 o'clock. Thank you.
Okay.
Thank you very much.